Hello everyone. My name is Xiaorui, and I will be going over the discussion 6 mini lecture, which is about ordinary least squares. Alrighty, let's hop right into it. So this week we looked at multiple linear regression, which is an extension on last week where we started off with simple linear regression. To contextualize what OLS is, it is basically an extension of SLR. And as a reminder, SLR allowed us to model some predictions that we wanted to make with these two features here, where we included an intercept term as well as one of our features, maybe from a pandas data frame or something like that. Now we're actually extending our model to be able to accommodate for as many features as we want to add. And the reasoning behind this is sometimes we want our models to integrate multiple relationships between the input data and the predictions we want to make. So as the bullet points here demonstrate, any xip represents a feature of our data set. So this would be like a column name. Any theta p represents a parameter of our model. This is what we want to optimize for to get the best predictions. And y hat represents the y value that our model predicts for one observation in the data set. Now that we have multiple features, we can express our predictions as a dot product of vectors, where the vector theta is just a vector of all our thetas combined together, and xi is a vector of all our different features for one observation. You may notice that xi has a 1 here, which doesn't correspond to any feature of our data set. It actually corresponds to the built-in intercept term that we always want to have. And this is what the dot product equation looks like. Alrighty. So most of the time we'll have many predictions that we want to use in our model, or many observations we want to use on our model, and we'll want to use these observations to make many predictions. We can organize all of this data in a design matrix. So here we see that this is our features, this is our parameters that we solve for, and this is our outputs or prediction. You could see that this is basically a lot of vectors on top of each other. And you can imagine that this, where all our features reside, come from a data frame of selected columns. And then after we multiply this matrix with the params we pick, we should get the predictions we want. One important thing to notice is that any prediction that we make has to be a linear combination of the columns in the X matrix. So we could say that y hat is in the span or column space of X. And in other words, we can add up some combination of the columns of X to create y hat. And why this is important is it basically restricts us to choosing our parameters to optimize for the span of X. We can't just add arbitrary data in some areas of our matrix to make our model better. We have to go off what is given to us in our design matrix. From this point on, I do want to point out that we'll be using a fair bit of linear algebra. If you need a refresher or taking a linear algebra class concurrently, Bella, who was a past head TA, compiled her favorite resources here. You'll be able to find the link in the PowerPoint. The general important topics are just vectors and matrices in general, orthogonality, projections, norms, linear independence, rank, and invertibility. And to add on some other important topics, you'll want to refresh on chain rule, as well as things like the power rule and finding mins and maxes. Alrighty. And I do want to emphasize that we are always happy to help out with any concerns regarding prerequisite knowledge. So going back to OLS, to make the best possible model, we want to choose the values of the model parameters theta that minimizes loss. For our mean squared error loss, which is a specific loss function, our best guess for the true y vector is the orthogonal projection of the y vector onto the span of x. We can use this fact to deduce the optimal theta vector. So what this is saying is on the image on the left, we could see that our predictions can only be in the span of x. So this flat plane over here represents the span of x. Theta hat is our optimal parameters, and we can only ever choose a y hat that is on this, flat square. Um, our true values, though, our y values, might actually not be in the square. If they were in the square, this would suggest that we could fit a perfect model. But in the real world, obviously, you're probably never going to get a perfect model due to all the noise, all the variance in your data collection, things like that. So it might lie beyond the span of X. So what we want to do is we want to optimize for some distance, right? And it turns out in our MSC loss, this is the orthogonal projection, which means um, the residual vector creates a 90-degree angle with the span of X when moving down from our true values. In lecture, we derived that this optimal value is actually this closed form solution. And I suggest watching lecture to, get into that derivation a little more. And it is this theta hat that minimizes the L2 loss. So it's also important to note that this closed form only applies to if we're using L2 loss, and you'll see that derivation in lecture. What all of this math means is that we're finding the least value of this square loss. Pretty much since we're minimizing the distance, this is our optimal solution for it. To dig more into the closed form solution, this is really important to know. Don't worry, you don't have to explicitly memorize it since it will be on your reference sheet, but it is one of the core equations of this class. Some things to note is that this intersection, or intersection, not intersection, is only works when XTX is invertible. And this, as mentioned in lecture, only occurs when all the columns are X are linearly independent. We could see that this inverse is actually what, bottlenecks this whole process. Another thing to note is since this is, pretty mathematically rigorous as compared to, some of the more coding-based stuff, you might see some questions where some combination of variables are lumped into a linear algebra expression. Don't panic when you see that. Try to go slow and methodical and recognize combinations of matrices that you know. So let's say if you see this entire term on the right side of the equation in a midterm, you could substitute it for your optimal theta hat as a way to simplify the expression. So just take things one step at a time when you see those type of questions. Alrighty, speaking of loss functions, since this closed form solution only works with L2 loss, in data 100 specifically, we'll mostly look at two loss functions. So mean squared error is probably the one that has been mentioned the most. It is when we subtract the guess from the true y. So the true y is the y that does not have the hat on it. This is the true y subtracted by our guess, and then we take that and we square it. After that, we add up every single loss from the data set, and then we take the mean, which is basically what is happening here with the summation and multiplying by 1 over n. An open question I'll leave for now is how this process differs from the mean absolute error and what impact it might have on the error. So the mean absolute error is pretty much a very similar thing. Instead of squaring the difference. We are just taking the absolute value. And going back to my open question, what you'll notice is that the mean squared error actually uh, punishes mispredicting greater more. And what, in other words, if I had a true value of, let's say, 4 and I predicted 1, my mean squared error would give me 9 for that point. Whereas for mean absolute error, our error for that single point would only be 3. So mean squared error actually punishes mispredicting wrongly more, further away more. And remember, for all our models, we want to design uh, our betas to have the lowest loss possible. Um, that's just something that is intrinsic to creating a good model or a good model mathematically. Alrighty, so this is an example of what you'll see on your reference sheet. You could see that you don't have to worry about memorizing the specific solutions to these things, such as for SLR and MSC, you get the closed form solution as well as OLS. Alrighty. To cap it off, I have a slide at the very end talking about the big picture. The design matrix is a matrix where each row is an observation of the data set and each column is a feature. So why do we care about that? The design matrices represent the data and we could use them to efficiently build models. The residual is a vector representing the difference between the observed y and the predicted y for each observation. And why do we care? This basically encapsulates how good our model is. A good model will minimize the norm of the residuals, making the error as small as possible. And OLS is a technique for choosing model parameters by minimizing the norm of residuals. And why do we care? OLS is the backbone of multiple linear regression. It builds the best models we can make. And I've also included some math facts here at the bottom that you could review. These should be mentioned in lecture. Some of their derivations might be out of scope, but the facts themselves are in scope. Alrighty, thank you.